Hello everyone. Today I will be speaking of the importance of past climates to understand the future. My name is Julien Emile-Geay. I'm a professor at the University of Southern California in Los Angeles. And some of the material in here comes from multiple sources, including the work of a graduate student at UCLA called Steve Cropper. And also, I shamelessly lifted the title of this article the title of this talk from an excellent article by Jess Tierney at the University of Arizona, and I wanted to acknowledge that from the outset. So let's get into some motivations. Why study past climates if what you most care about is the future? And the first motivation really is to provide context. When we look at the past 150 years, we realize that they are woefully short to evaluate whether there might have been any precedents to, for example, the rapid warming trend that we have witnessed over the past 50 years or so. So in this figure from the latest IPCC report, we see this relatively short picture. But now we actually have enough information to fill in the blanks basically over the past 2,000 years. And I was personally involved in two of the reconstructions that went into this estimate there. Don't think you should look at those uncertainties too seriously. I think they tend to underplay what's really going on. But the point here is that there does appear to be an unprecedented level of warming and unprecedented rate of warming in the past 2,000 years. So providing context at various timescales, not just 2,000 years, but perhaps 10 million years or 100 million years, is really vital, because one of the favorite excuses for inaction on climate change is that the changes we've witnessed recently are part of a natural cycle. Another really important goal is to hunt for analogues in the past. And indeed, you can sort of see this at the very end of this particular graphic. When we look at projections for the future, we see that depending on, of course, many variables, but in perhaps some of the more emission-intensive scenarios, we are looking at a global temperature warming that is maybe 5 to 10 degrees Fahrenheit warmer, or something on the order of maybe 3 to 5 degrees Celsius warmer than the present. And this is not something that we have witnessed recently in the recent past. In fact, we would probably have to go back and rewind the climate clock at least 5 million years before we see anything on the order of the changes that we are expecting. And so it might be actually really important to look at climates like the Pliocene, to see how, for example, several organisms, several classes of organisms behaved under these conditions as a sort of natural laboratory, if you will. So using past climates as a natural laboratory to understand the resiliency of ecosystems and things of that nature. And we could actually do this as well to understand the resiliency of human societies. So perhaps not in relation to much warmer climates, although there is definitely some overlap between warmer climates and human history. But for the vast majority of the history of our species, which depending on who you ask is, for Homo sapiens, it's perhaps the last 200,000 years. If you want to look at hominids, it's the past 4 to 5 million years. There have, for the most part, we've lived in colder conditions than now. So, but there are interesting analogs that we can find in the paleoclimate record for example, drier conditions or examples of abrupt climate change, like this one here that's labeled YD for Younger Dryas. And those are very instructive to teach us how human societies can fare in the face of various kinds of climate change that we may anticipate. So that's the second major motivation for studying past climates, I would say, is finding analogs for changes that we might expect. The third one is to actually constrain the processes themselves. And there's a quote here that is taken from this article by Jess Tierney. And particularly, I think in the past 5 to 10 years, there has been a renewed interest for using paleoclimates in constraining several processes or several variables that can be difficult to constrain based only on the information that we have over the short instrumental record. So when I say instrumental record, what I mean is the era of instrumental measurements, where we basically had things like thermometers, barometers, and so on to monitor the climate system. And before that, we have to make do with indirect information, and I'll get to that in a second. But basically, in this review, the point was made that the paleoclimate record is now rich enough, and there's enough understanding and overlap between different data sources to start evaluating how certain climate models, for example, simulate these past conditions, and particularly, constraining processes like certain cloud processes that can be very difficult to constrain over the instrumental record. But if you rewind the climate clock to, let's say, the early Eocene, as is shown here, where it was much warmer than now, then you're basically taking your model, which, as I'm sure you have seen or you will see in this Climate Match Academy, the models are the basis of our prediction. And we definitely want to take these models on a test drive and see what they're made of, see how they behave under fairly different conditions, and see if, for example, the simulations we have of processes involved with clouds behave realistically in the past. And the best way we have to do that is basically, can they reproduce changes that we know occurred? So that would be the third. And I'm not going to be able to touch on all three motivations in this relatively short lecture, but I'll do my best to give a hat tip to at least two of them. So my specialty has actually been looking at the recent paleoclimate record, particularly what we call the Common Era. So the Common Era is the past 2,000 years of Earth history, and it overlaps, of course, a lot with human history. And I find it a really rewarding area to work in because of that intersection, because of the fact that there's a fairly high density of climate data sources that we can rely upon to draw a global picture, or even sometimes a fairly detailed regional picture of what happened, which is not something you can do in the Cambrian era, for instance, where you're lucky if you have one record and you basically try to extrapolate to the rest of the globe. But also there is this intersection with human history that can teach us a lot. And so perhaps some of you have heard about the hockey stick. That is the nickname given to a very famous reconstruction of the global climate of the past 1,000 years that was originally published by Mann, Bradley, and Hughes in 2 articles in 98 and 99. And basically the statement that they made was that at the warming observed at that time, sorry about that, was unprecedented in the past millennium. And this generated a lot of controversy at the time, but it also became an emblem of global warming for many people, and generated in the US no fewer than 2 congressional inquiries. So it became a little bit of a lightning rod for several public debates about climate. And there are definitely, this was a pioneering study, definitely trailblazing, but it was based on relatively unsophisticated statistical methods. That was definitely the conclusion of one of those reports. And the data at the time were also pretty sparse. And so what I'll show you today is some recent improvements upon this seminal work by Michael Mann and co-authors. So a lot of this was actually published in 2019 in a consortium paper. So the PAGES2K Consortium is a sort of volunteer organization of members from all over the world. It was based on a larger consortium actually that assembled a global proxy database. And based on these proxy data, which I'll explain what I mean by that in a second, we applied 7 different statistical methods to the reconstruction of past climates. So what you see here in these colored curves are 7 estimates and their uncertainties of what we think happened to global temperature over the past 2,000 years. And again, at the risk of spoiling the suspense, you see basically some kind of hockey stick. And this is ostensibly what is summarized here in that IPCC figure that I showed before. So that IPCC figure was basically taken from that particular study. So what I want to do over the next few minutes is basically walk you through how we did this, get a flavor at least for what went into constructing curves like that. So we don't have thermometers, as I said. So what do we have? Well, what we have are things that we call climate proxies. So what we mean by a proxy is a stand-in for the real thing. So if you think, for example, of a legal proxy, it's somebody who goes to represent you in court if you are unfortunate enough to face that circumstance. And a climate proxy is a system, whether it be organic or inorganic. So it could be a living organism like a tree, or it could be an ice cap, for instance, which is not living. But regardless, these are systems that are sensitive to changes in climate, and they record it in some way. So for instance, the tree, if you pick a tree in judicious places, the growth of the tree tends to be limited by certain factors that are related to climate. So namely, temperature during the growing season is a limiting factor for the growth of many trees at high latitudes or high elevation. So one thing you can do is by carefully selecting where you pick the trees, you can basically get them in environments that are marginal for growth. And that way they will be sensitive indicators of climate. When climate conditions improve, when temperature increases, basically, then the tree is happy and it lays down a relatively thick ring. But when climate conditions are colder, it will lay down a narrow ring. So by inspecting the pattern of growth in a tree like this, you can get an idea of how the temperature has varied. And then we have a lot of other archives you may not have thought about. Perhaps you've heard about ice cores, and you know that we can measure all kinds of things in ice cores, including the air bubbles containing information about the past composition of the atmosphere. This is partially how we know, that CO2 concentrations have not been this high in at least 1 million years. But there's a lot of other information that's contained in the ice itself, in the water, the frozen water molecules that constitute the ice. And for example, the isotopes, so I'm not going to get into the details of that, but for those of you who know a tiny bit about nuclear physics, basically, you know that chemical elements come in different avatars that have the same number of protons, but differ in their number of neutrons. Some of these nuclides are stable. So for example, there's 3 kinds of stable oxygen isotopes, oxygen-16, which is the most common, but there are also avatars of it, oxygen-17 and oxygen-18, that have respectively 1 and 2 more neutrons, than the standard oxygen atom, which has 8 protons, 8 neutrons. And it turns out that you can measure, for example, these oxygen isotopes in a lot of different systems, in ice cores, in sediment cores, in corals, in speleothems, and that they almost always have something interesting to say about climate. So that what they say about climate may not always be exactly temperature, but in general, it is affected by temperature. So that's just one of the many examples of data streams that we can collect from these various archives. I probably won't be doing justice to the enormous area of scholarship that has gone into this. It's taken many decades by many very dedicated people to actually probe the sensitivity of these various systems to climate and to develop what we might call paleothermometers, ways to devise, ways to infer the temperature in the past, at the time where these archives were registering climate. And so that's just a very quick overview of how we do things, but those are basically the ingredients of what we put into these reconstructions. And so we also have to be fairly clever about how we date these things, because often we don't know a priori. But one of the reasons why the Common Era is relatively easy for that is that we can, in many cases, count layers. So it's not always possible, but in many of these cases, they are annual layers that are laid down, whether it be coral reef growing year by year, same thing with a tree, or it could actually be an ice cap where there's a seasonal cycle in the amount of snow. That means that you lay down rings piece by piece. And that basically, by counting back from the top, which you can usually assign a date to, by counting backward, you can figure out how much time has elapsed. The process is not error-free, but by replicating it, by, for example, counting many nearby trees, you can really beat down the uncertainty. And so in many cases, that uncertainty is close to zero, and we have what we call annual resolution. That is to say, we know what happened within a year. And so in this work that we did, so this was published in 2017, this is a global database that was assembled by close to 100 people, volunteers, all of them, like myself. And so we had about 700 records from 648 locations. We had some very high resolution archives, like some corals that had basically biweekly records, to some sediment cores where we had closer to a centennial resolution. You can see here that we draw from 11 different classes of proxies. Some of them were short, some of them were long. But basically what they all had in common is that all of these had been identified as bearing a temperature signal. And there are challenges in working with a database like this. You can see that the availability of these proxies decreases back in time. But lo and behold, that's the input into all of these reconstruction methods that I mentioned. And so what do you do with that? Well, the simplest thing you can do with that is what we call composites. Perhaps that will be one of the activities that you will work on during this academy. Composite is the simplest form of statistical treatment of a time series. You basically average them together. And basically in this figure, again, from this 2017 article, we showed that it doesn't really matter how you slice or dice the data set, whether you screen for certain things, whether you look, whether you separate the high resolution records, which are written HR here, versus the low resolution records that are written, that are denoted LR. Basically, every single time, depending on how you bin them, you get the same answer, which is a hockey stick, which is that the conditions had been relatively stable early in the millennium, and there was this cooling trend, and that it appears that the Industrial Revolution basically reverted this cooling trend fairly rapidly, so that we end up with this hockey stick. Now, I was involved in several efforts, two of them actually, that were devoted to reconstructing or developing methods to more accurately or more fully reconstruct climate conditions. So this is just one of many, and I'm not going to get into this. This is using a data assimilation framework, a Kalman filter, for those of you who are familiar with that. You don't need to know the details of this, and I apologize, the equations actually got a little bit mangled, so you should not look at them anyway because they won't tell you anything. But lo and behold, the idea is that we can use these paleoclimate proxies as inputs. And in this particular method, we actually fuse climate models and climate proxies together to get a global picture of past climates. And we did this, and you can basically validate what the method does, and you can show that it actually agrees really well with instrumental estimates. You can do this over space as well, which is what this map shows. Basically, everywhere that this map is red means that we are actually doing pretty good. The redder, the better here. So there are areas, particularly over the Southern Ocean, where we have very poor proxy coverage and where we do very poorly. at reconstructing climate. In fact, we do so poorly in some areas that we don't even try. That's the meaning of this gray area. But this is one thing perhaps you will be playing with in your practicums, is the last millennium reanalysis. And I'm very fond of visualizing it in all kinds of ways. What I find most interesting about it is that basically this gives you a history of the probability density of climate over time. So if you're a fan of Joy division, this is maybe how you would visualize it. So over the recent time, by definition, 0 corresponds to the present in terms of like average conditions. And you can see that as we went back in time, we had different cooling and warming episodes, but also that the width of these statistical probability distributions has increased over time. And that's a reflection of the fact that we know the past less well than the present. So the further back we go, as a general rule, the wider the uncertainties are. And I think these visualizations do a good job of representing that. Not all of the methods, statistical methods that are used actually have that feature, but this one does. I'm going to pass very quickly over this. Sorry again, the equations got ruined by Google Slides, but I swear they're correct in this paper by Barbosa et al. And that is also some work I was directly involved in. And in this, we basically were able to use the paleoclimate record to diagnose the influence of various forcings. I trust that the term may be familiar to you now. So the influence of greenhouse gases, solar and volcanic forcing. And basically what we find, and this is a claim that's very often made in the literature, is, maybe the fluctuations we've observed over the past century or the past millennium, they're due to changes in solar output. And you can put that in, and basically what you find is that that's indistinguishable from 0. It's this green curve over here. It means we don't find a detectable influence of solar activity. We do find a detectable influence of volcanic activity, that is this yellow curve there, and we have a good physical understanding of it. But of course, the biggest influence is greenhouse gases. So that's just one of the many ways in which we can, beyond the shadow of a doubt, establish that the human hand in climate change. So that's basically, to wrap this up, how we produced at least 2 of these reconstructions. What I showed you today is basically the one in brown and the one in cyan, which kind of bookend these reconstructions. If you're interested, you can look at this paper for details, but this was just a little vignette to sort of show you what goes into reconstructing climate over the past 2,000 years. Basically, it takes a lot of different proxies that have been collected by a lot of dedicated people over a long period of time. And it takes different statistical methods to try and squeeze a signal and a measure of uncertainty out of this. And in many cases, the uncertainty is at least as important as the curve itself. So if you remember anything from this lecture, may it be that. All right. Finally, I want to talk a little bit about constraining climate sensitivity. You may not actually have heard about it at this point, so I'll briefly introduce it. My academic grandfather, Jules Charny, in 1979, actually chaired a National Academy of Sciences report that looked at the impact of CO2 on climate. And in it, they introduced this notion called equilibrium climate sensitivity, which is defined as roughly the level of warming that would ensue if you doubled CO2 concentrations from its pre-industrial value of 280 parts per million to 560 parts per million. And in that report, based on very limited evidence, Charny and the panel concluded that we would observe changes on the order of about 3 degrees, with the best estimate of about 2 to 4.5 degrees. And it turns out that in the 45 years or 44 years since that report, that particular picture has not changed very much. So this is a representation of this quantity, ECS, equilibrium climate sensitivity, as portrayed in this Charney report that I just mentioned, and also how it was assessed in many of the IPCC reports, including in the latest IPCC report, there's a number of models that actually had fairly high climate sensitivity of higher than 4 and sometimes as high as 5 or 6. And one of the reasons why we care about this is that basically if climate sensitivity is very high, then for a given amount of carbon dioxide in the atmosphere, it will warm up a lot and we don't have much time to act on climate. But if climate sensitivity is low, then there isn't as much urgency to act on climate. So this is literally $1 trillion problem. Some people have said, that by better constraining this one number, that would save trillions of dollars in investments, that, would provide a lot more clarity, how much time we have to deal with climate change. And the thing is that there have been many studies, some of which are summarized here. This was from a review paper by Knuthi and Hegel in 2017. Since then, there have probably been a few dozen other studies. And basically what all of these color bars show is various estimates of equilibrium climate sensitivity from various sources. And you can see that in general, many of them have very, very large uncertainties. But the hope is that we can basically narrow all of this, that by combining perhaps several sources of information, we can narrow these uncertainties. And so I'm going to pass quickly on this, but some people have done this with satellite data. Some people have done this with ground-based observations. Some people have attempted this with general circulation models. There's a whole slew of methods that have been thrown at this. And the long and short of it is that basically over the past 45 years, that number has not been better constrained, which is extremely frustrating for those of us who are climate scientists. So one way in which you can actually constrain an unknown quantity is through something called emergent constraints. So the whole idea of emergent constraints is that you take something that you don't know, like ECS, and you tie it to something that you do know, that you can observe. So for example, well, I'll give you an example in a minute. But to date, more than 50 examples of emergent constraints have been proposed. You can't just pick any quantity, but it needs to be something that makes physical sense. For example, something that might scale with ECS would be the intensity of heat waves over a particular area. Ideally, this is something that's exhibited by several climate models, for instance, because this has been applied a lot in the climate model realm. And we often encourage out-of-sample testing to show that it's not an artifact of that particular selection of models. And so here's one example from work by Martin Renou and collaborators, where they basically looked at constraints that were offered by data from the last glacial maximum, which happened 20,000 years ago, as well as the mid-Pliocene warm period, that is, somewhere around 3 million years ago. And basically what you see in green here, these curves are probability distributions on this elusive number of climate sensitivity. And the dashed curve represents what in Bayesian statistics we would call a prior. So that's your a priori notion of what it is. And you can see it's sort of peaked around 2.5 or 3 degrees, but it's very broad. We can't exclude something as low as 0 or as high as 8. That's the prior, and priors are a mainstay of Bayesian statistics. I'm not going to get into the details, but they're basically a way to encode your knowledge or lack thereof. And so in this case, we'd have a little bit of knowledge independent of the paleoclimate record. We just know the general range of climate sensitivity, we just don't know exactly. And basically, once you put in some observations about how much we think it cooled at the last glacial maximum and what the models say happened, you can basically derive some kind of regression line, and from that you can improve your estimate. So it's not, a single line. It's still a fairly broad peak, but at least now we have something that's, closer to, that's a little bit more well defined. And it turns out if you do this over the mid-Pliocene warm period, you get a much tighter regression line, and so a more well-defined peak. It's perhaps not obvious here, but for example, here you can basically exclude climate sensitivity above 5 degrees, whereas in this case, it was a little bit harder to do. And the magic here is that you can actually combine these two sources of information. So the last glacial maximum here would be this blue curve. The mid-Pliocene warm period would be this orange curve, and by combining those two sources of information, you get a more focused distribution. So paleoclimate data can basically help reduce the spread of ECS. And in some of our own work, we've done this. We've applied this to temperature over the common era. So I'm going to pass on this because I can't do justice to it, but there's basically a metric of temperature variability that's called psi, that can be related to ECS by this fairly simple theory. So that's the predicted emergent relationship. And we can basically, we can't observe ECS directly, but we can observe psi. And that was done by Cox et al. Over the instrumental period, but unfortunately they had pretty big uncertainties because the instrumental period is very short. So that limited the statistical confidence. And in work that's now in review, we actually applied this to these reconstructions of the common era that I just discussed. And based on this, we get some fairly noisy reconstructions or fairly noisy constraints. But again, by combining them with different sources, what we can do basically is exclude very high values of climate sensitivity. Basically, what this shows is that climate sensitivity is perhaps in the 2 to 3.5 degrees range, but certainly not 5 or 6 degrees. So again, we're back down to Charney's original result of something around 3 degrees. We find 2.8, but more confidence because we have many different independent sources of information. It's time for me to conclude. So what I'd like you to remember here from this lecture is that past climates are extremely relevant to the future. To paraphrase Churchill, the further back you look, the further you are likely to see. And the way this works out with climate is that you are able to diagnose and understand the behavior of the climate system over a broad range of states, much broader than what we've seen so far over the instrumental era. Remember that this information comes from very diverse sources, diverse archives, diverse proxies, as in the types of observations that are made, diverse people. In the work that I showed you, there were more than 25 countries represented, and diverse expertise. To be able to do this, you need people who go to the field. You need lab scientists to actually take the measurements. You need data scientists to assemble it and analyze it, and you need modelers to model the climate and basically come up with a coherent picture of what happened. So we need diverse expertise. We need diversity in general. Diversity is good for science. And finally, what I want you to remember is that we get quantitative constraints on a number of things. So this is not just abstract wiggles disconnected from numbers, but we can actually quantitatively provide constraints on key climate variables like equilibrium climate sensitivity. And as it turns out, although I did not show it today, also on key climate processes. For example, what happens within clouds. And if you're curious about this, feel free to email me or check out my webpage, which is listed below. Thank you very much for your attention, and I hope you are truly enjoying this Climate Match Academy.